So I was trying to remember. So to my first contact with Lorenzo, so it was when I was PhD student, and so Lorenzo was here to support me for my first works I presented. So, and then I saw that in general, Lorenzo, I noticed your kindness and attention for young people. That was important for me. And then about your work, it has influenced me a lot. I learned a lot from your work. So my talk today is about joint work with Jérôme Buzzi and Omri Sarig.
Just a remark. I guess that the first time that we met, Michal were around, because I guess that at that time he was visiting Dijon.
Yeah, but maybe we met before, maybe in Porto, or maybe you visited Orsay, okay. You gave a talk in Orsay, so yeah, we had a few contacts, yeah. And yeah, so I was saying I will present some joint work with Jérôme Buzzi and Omri Sarig. There will be a second part, which will be the talk by Omri on Wednesday. But before that, let me comment a bit on some of your research, Lorenzo. So I've been influenced by many of your works, but I would like to quote one today. Yeah. So this one is a paper you wrote with Christian, and in the first paragraph, you wrote, one of the main problems in dynamical systems is to describe the limit set for a large class of diffeomorphisms. The ideal objective is to split the limit set into finitely many pieces of dynamics, which are mutually independent, maximal, and dynamically indecomposable. And the next step should be to give a description as complete as possible of each piece. And what I want to discuss today fit very well in this with what you said. So so before, let me explain a bit some history about that. So the problem here, there are two. One is to identify what we could call elementary pieces for the dynamics. And then the second part is to describe the dynamics inside. Okay. So some early work for hyperbolic diffeomorphisms. In this case, you have Smail's spectral decomposition theorem, which asserts that the non-wandering set decomposes into finitely many subsets, disjoint, that we call basic sets, that are a hyperbolic set that are transitive and locally maximal. And so it's a good, it's natural to take that as the elementary pieces in this case. And there is a way to build the basic sets. And so this is, yeah, there are the homoclinic classes. So if you take one hyperbolic saddle inside one of these sets, you can get the whole set by considering the stable and the unstable manifolds of this periodic orbit, taking the transverse intersection between these manifolds, the closure, and then this is a homoclinic class, so introduced by Newhouse. And this set is good because, so in the hyperbolic diffeomorphism, it is a basic set, but you can also define this for any diffeomorphism once you have a hyperbolic saddle, and you will always find a transitive set, and periodic points inside are dense. And so you can play with these periodic points and try to get to prove some properties on this set, further properties. And so this is something you did with several people. So for instance, you played a lot with C1 generic diffeomorphisms. So this was the topic of this paper I showed. So the goal was to find the species, and the candidate was to look at the transitive sets that are maximal for the inclusion. And so C1 generically, there were several people that I list here who worked on that. It is the case. So the homoclinic classes are maximal transitive sets, and in fact also maximal chain transitive sets. So this was playing with connecting lemmas results, several versions. But in the paper I showed before, in fact, you also proved that the homoclinic classes are not the only maximal transitive sets or chain transitive sets. Even generically, you will also have sets with no periodic points that later we call aperiodic classes. Anyway, for C1 generic diffeomorphism, we have a quite good understanding about these pieces, what we want to call elementary pieces for the dynamics. You have several candidates at first, chain transitive sets, and they coincide. Then you did other works about homoclinic classes, not only in the C1 generic world. So you consider the bifurcations of these sets, collisions, explosions, again with other colleagues. So very well. And so, as I said, the second step of the program now is to understand what happens inside these classes. How much can you describe the dynamics inside? And so the natural thing to do at first is to consider the periodic orbits, since we know this set is filled by periodic orbit, and then there are, you have transitions orbits between them that can connect this periodic orbit. And so there were, you did a lot on that, and then there were many works in that direction, which uses the periodic orbits. For instance, this was crucial in your work on robust transitivity with Enrique Pujals, Raúl Ures, and Christian Bonatti. Yeah. So today I would like to present results that also go in this direction, that explain how to describe dynamics on a homoclinic class, and I hope you will like that. So I will concentrate on surfaces, okay? But let me go back to the first part of the program in the case of surface dynamics. So the spirit is the philosophy is to consider an arbitrary diffeomorphism of surface. I will assume it's infinity, so not generic. And let's try to decompose the dynamics. So here is some result we proved with Jérôme and Omri before the work I will present today. And we incorporate and restate a famous result by Katok, which gives some spectral decomposition for these dynamics. So it says that the homoclinic classes are the good pieces for spectral decomposition in this setting, provided you trash some small set of the dynamics. So you will trash sets which carry zero entropy. So if you do that, if you take, for instance, any measure with positive entropy, it is supported on one homoclinic class. Okay, so the union of homoclinic class cover all the dynamics with positive entropy. And then, well, you pointed out that homoclinic classes in general are not disjoint, and so you have this collision that could occur. Anyway, if you concentrate on set with positive entropy, when you have two homoclinic classes that differ, in this setting, the intersection always has zero entropy. Okay, so they are essentially disjoint. And then for hyperbolic diffeomorphism, you have a finiteness of basic sets. So you may wonder if here you have also finiteness, and you won't have because you have, for instance, Newhouse phenomenon. And anyway, you can recover some finiteness. So here again, you filtrate it by entropy, and the result is that above any number, the classes whose entropy is larger than this number, positive number, then this set is finite. Okay, so this is, in this sense, a good spectral decomposition.
Sorry, Sylvain.
Yes.
The second statement in the theorem, you are saying that if the homoclinic class one is different from the other one, and then
yes,
the topological entropy is zero on the intersection. But excuse me, but in this case, they do not coincide. Do you remember that?
No, so you may have, for instance, two homoclinic classes that touch just at one fixed point. Even
okay.
Yeah, so these are a small set. You may also imagine a dynamics on surface. So for instance, a torus, and then you have two half tori separated by two invariant circle, and you feel there's two half tori by two homoclinic classes that are independent and touch just at this invariant circle. So the intersection is a circle and does not are two circles that do not carry entropy. Okay, but this set are small.
Sorry, but I forgot my own theorem with Morales and Carvalho that we just proved that the homoclinic classes either are disjoint or coincide. And then what is the difference?
Generically, you prove that generically.
Okay.
Yeah. So that's this is the point here. The goal is to say something for any diffeomorphism.
Okay. Thanks a lot.
So, but let me ask you, so what if you have two basic sets in which are related in this mail order? Aren't they?
Yes. Well, they are related by heteroclinic orbit. Right. That does not belong to the homoclinic classes.
Right. So, and then, there might be lots of points, right? I mean, there could be a transverse intersection.
Yes, in one direction.
And then the entropy is zero.
Yes. Mm-hmm. Yes.
That's included in your second item here, right?
Yes, if you have transverse intersection in both directions, then the two classes coincide.
Then it's only one, but
only one. Yes.
Ones.
Yes, but this heteroclinic orbit does not appear, is not in the intersection, or maybe not in the intersection. Right. Yes. Yeah. Just to say, we are on surface, positive entropy for a measure imply that this measure is hyperbolic. So behind this result, it's a description of a set that what we could call the non-uniformly hyperbolic set. So a restatement is that if you take an ergodic measure which is hyperbolic and not just one periodic orbit, then this measure is supported on one class and only on one class, cannot be supported on two different classes. Okay. So this is the goal today, is to focus on the set that we will call the non-uniformly hyperbolic set and try to describe the dynamics on this set. Okay. So how to describe dynamics? One way is to do some ergodic theory. So there are several ways to do ergodic theory. Today, I will focus maybe on one of the simplest cases, which are measures maximizing the entropy. So we know we have the variational principle. We know the entropy on measures approximate the topological entropy of the map, and we wonder if there are measures which realize the topological entropy. If this is the case, these are the measures maximizing the entropy. So what do we know? For hyperbolic diffeomorphism, we know that these measures exist. This supremum is attained. Their number is finite because on a basic set, you have at most one such measure.
So we're talking C infinity here, or?
No, I am talking about hyperbolic diffeomorphism for the moment.
Oh, I see, sorry.
Yeah, and as a motivation. And then there's measure are natural in the sense that if you, for instance, consider periodic orbit with larger and larger period, you look how you average along this periodic set and you look how it distributes, and it goes towards a combination of these ergodic measures maximizing the entropy. Then the dynamics, the measurable dynamics of this measure, we understand it well. It's more or less a Bernoulli measure, isomorphic to a Bernoulli measure. In fact, you may have some period, a homoclinic class, a basic set may have some period. It may be decomposed sometimes into several pieces that are cyclically exchanged by the dynamics. And so the measure is isomorphic to Bernoulli times a cyclic permutation for this period. And if you want to have finer properties, you can show an exponential mixing or decay of correlation, exponential decay of correlations. So for that, you need first to assume mixing. So you need to consider the case of a basic set with period 1. So if it you won't have period 1, you take an iterate of the map in order to check that. And so so in this case, when you take two observable, other observable, and you look to their correlation, this decays exponentially fast with the dynamics when you push by the one by the dynamics. Okay, so this is very well known for hyperbolic diffeomorphism, and what we want to do is to describe that, to ask if this also occurs for arbitrarily surface diffeomorphism. And so this is the content of the theorem of today. These properties are also satisfied on surfaces by C-infinity diffeomorphism, provided the entropy, topological entropy, is positive. In fact, when the entropy vanishes, it's a completely different world. You have more rigidity. But this is something, for instance, I studied with Enrique Pujals and Charles Tresser. You have a completely different description. So when entropy is positive, you have these 5 properties. So the first one has been proved by Sheldon Newhouse 20 years ago, maybe, using Yomdin theory. About periodic orbit, this is a theorem by David Burguet. In fact, you have to precise the statement. You cannot just take all periodic orbits. You have to restrict to periodic orbit whose Lyapunov exponents are good enough. So larger than some epsilon, small epsilon that you fix. The property 2 and 4, this is something we did with Jérôme and Omri in the same work as the spectral decomposition I presented before. And so what I would like to discuss today is the 5th property about the exponential mixing. In fact, I won't comment on exponential mixing today. Today, I will do some preparation, introduce some properties, and then Omri will derive this property on Wednesday. Okay. One warning. Here, I really need that the diffeomorphism is C-infinity, and when it's for CR diffeomorphism, even for R large, there are counterexamples. For instance, Jérôme Buzzi showed that there are CR diffeomorphism that do not have measures maximizing the entropy. Okay, so to go towards this
Sylvain,
property, yes.
Can I ask a question quickly?
Yes.
These counterexamples, you said there's counterexamples to the existence, but are there counterexamples to the exponential mixing?
No, but if you don't,
okay,
no,
but I mean,
no, but you mean assuming this?
Assuming that a measure is of maximal.
Yeah. No, I don't know. I don't know that.
Okay, thank you.
Yes.
Thanks.
Okay, so behind this result, there is a property that I want to introduce and emphasize today. So this is what we call a strong positive recurrence. Okay, and as I said, I will concentrate on the non-uniformly hyperbolic set of the dynamics, which is the set that will carry all the entropy. So let me explain what I mean by non-uniformly hyperbolic set. Well, I will restate classical things on Pearson theory. So what is a Pearson set for me today? So a Pearson set is a set of orbits, of points, sorry, that that realize some hyperbolicity, non-uniform hyperbolicity. So I mean points which have a splitting of their tangent space into two parts, stable and unstable, such that the unstable, the stable is exponentially contracted forwardly, and the unstable is exponentially contracted backwardly. Exponential mean you have some exponential rate, which is chi. So you fix some chi. And you need a constant also, which is c. So starting from the point x, you see this exponential decay in the future, in the past. But not only that, you need that along the orbit, you will also have good estimate on the exponential contraction and expansion. So of course, when you shift along the orbit, you will have a similar estimate with other constant c. And you don't want the constant c to be too bad when you iterate. So what we require is that this constant c degenerate only slowly. And so you incorporate a new control, which is this epsilon k. So you take some small epsilon that that control how this constant c evolves when you iterate along the orbit of this point. So the point that satisfy this estimate are from a good set that we call Pearson set. So in general, in classical Pearson theory, what you do is to fix a measure. You take chi smaller than the Lyapunov exponent of the measure, and then the Pearson theory tells you each time you find a small epsilon, then you can find a c such that defining such a set, you will have a set which has large measure, as large as you want. Here, we don't want to specify the measure, okay? So we fix a chi, and then epsilon has to be small enough. If you don't take epsilon small enough, then you lose good control. So epsilon has to be small enough. I don't say how small, but small. And with small epsilon, then you deduce that at a point, then this splitting has to be unique. And then you have this well-known property that you have stable and unstable manifolds. The stable and unstable sets of these points are stable and are some manifold. And the set of points that satisfy these conditions for this choice of constant is a compact set, non-invariant, because when you iterate, this constancy varies. So it's a compact set. And I said the diffeomorphism may have infinitely many homoclinic classes, but when you look to the trace on one of the Pearson sets, you can only find a finite number of them because points in this set have stable and unstable manifold that are quite uniform. And so if you have 2 points close, then their stable and unstable manifold are related. And so these points should belong to the same homoclinic class.
So you also get largish stable and unstable manifolds. You get them to be fairly...
Yes, yeah, I didn't say they vary continuously on the set for the C1 topology, for instance.
Mm-hmm.
Yeah, exactly.
Sylvain,
yes.
The last property of the intersection with only finitely many cases is not true. You have only C1 topology, I suppose.
Yeah. So here I said R has to be larger than 1. Yes.
Just to know.
Yeah.
You can define the set also for C1, but probably the conclusion is...
And even the stable and unstable manifold do not exist for some particular C1 diffeomorphism. This is something we built with Christian and Katsutoshi Shinohara. Yes.
Okay, you are assuming the existence. Okay,
yeah. Okay. So what is the non-uniformly hyperbolic set? You say, okay, you want to take the union of these Pearson sets. But sometimes you really need epsilon to be small enough, so it's better to define it in this way. So to take some intersection over epsilon. So to simplify, let's imagine that you fix chi, you take epsilon really small, and in the future, what will interest us is how C varies. So why? So in this sense, the Pearson set filtrates the non-uniformly hyperbolic set. And when C increase, you will incorporate more and more weak points. And so the complement of this Pearson set is tells you, measures the lack of good hyperbolicity. Okay, so we think
Sylvain, you wrote as C goes to 0, but you mean C goes to infinity?
yes, yeah. Well, it's I'm not precise enough in this sense, in this sentence, but you understood. So we really think.
Set?
Sorry.
It is not compact set.
Lambda is a compact set, but the non-uniformly hyperbolic set is not. A priori, okay. And okay, you may have homoclinic classes, which is inside you have an increasing union of such Pearson set, but at the limit you will accumulate on a fixed point, which may be tangent to identity, for instance. So what we think to this Pearson set as a topology on the non-uniformly hyperbolic set, which is finer than the usual topology on the manifold. Okay, so going to infinity in the non-uniformly hyperbolic set is saying that we escape from any Pearson set. Okay, and so what we want to do is to say that we want to control how much on the dynamics remain outside the Pearson set. We want to control this decay to infinity in this sense. So for that, we introduce a property that we call strong positive recurrence. So we say that a diffeomorphism is strongly positively recurrent, or SPR for short, if we have a constant chi. So we fix the bounds on exponent once for all, and we say something for all epsilon. As I said, we need some time to have epsilon very small. So, but let's focus on what comes now. We require that there exist so three numbers. So one is a number h smaller than the topological entropy. One here, the C defines the Pearson set, and tau is a value for measure. So here is a property. We want that for any measure ergodic whose entropy is large enough, so larger than h naught, then this entropy should give mass to the Pearson set defined by chi epsilon c, a mass which is uniform, which does not depend on mu, so which is larger than tau. So to restate it, we are saying that measures with large entropy do not escape to infinity in this sense, in this topology, in this Pearson topology. Okay. So why this name? Why this notion? In fact, there is a motivation for that. There were similar construction before. So the first one, maybe one of the first one, is in a theory of Markov chains over countably many states that have been considered by, for instance, by Gurevich and later by Sarig, by many other people. Then you have a similar definition. So you have a Markov chain over countably many states, and you think that the complement of a big finite set of states is a Bornology to infinity inside this Markov chain. And so you can state the same definition. One way to say it is that when you erase some state, when you forbid some state, then you have a smaller Markov chain, then the entropy should be smaller. Okay, when you erase a big compact set, a big finite set of states, the entropy in the complement should be strictly smaller. This is what is called SPR. The first time I think this name appeared in these settings. And more recently, there is some, well, probably there are cousin notions that appear in dynamics, geometry, I don't know. But here, I think to one in particular about geodesic flow on negatively curved manifolds. So the geodesic flow is hyperbolic. The problem is not about non-uniform hyperbolicity. It's hyperbolic, but you assume these manifolds are not compact. So you have a lack of compactness, but for another reason than R. You can go to infinity in the manifold. And so you want to bound the time you spend close to infinity. And Shapira-Tapi and later on Guezel-Shapira-Tapi have introduced a similar notion that they call also SPR. Okay?
Sylvain, sorry.
Yes.
Is there any relation between this definition and the slow recurrence to the critical point? Because this is like a counterpart.
Yes, so I don't know. I haven't thought in this way, but in some sense, here we are describing from inside the non-uniformly hyperbolic set. And what you say is, okay, you have a critical point which is outside and you describe from outside now. Yeah. But I don't know if there is a way to relate. It would be interesting. Then for some particular map, well, let's see. Maybe this is weaker, maybe, because you will see that it will occur quite often. Okay. So here is the result I want to comment today in this talk. So I want to show that any C-infinity surface diffeomorphism whose entropy is positive is SPR. So you see this property will occur often. Whereas I am not saying anything about the critical point and the recurrence close to it. And on Wednesday, Omri will deduce consequences of this property, in particular about the exponential mixing. Okay. So to show this theorem, I first state a criterion to guarantee that you are SPR.
Sorry, Sylvain,
Yes.
so there's one more question about the previous, all this discussion about the definition, and because I'm also very intrigued, because of course when you think of recurrence, you think of some kind of ergodicity, but this is nothing to do with that, right? I mean, this is a kind of Poincaré recurrence in some sense. It's not to do with ergodicity, right? I mean, because you may have something that is not ergodic that is strongly positively recurrent. Of course, in general,
we are considering all the non-uniformly hyperbolic set, which supports plenty of measures.
Exactly.
We are not
So
specifying this or this measure. Okay.
So this recurrence has more to do like with some recurrence within each ergodic component. So it's not related to any kind of ergodicity. Right?
Yes, not directly.
Right.
Yeah.
Okay, sure. Thank you.
Okay, so let me give a criterion to check the SPR property. So the SPR property has something to do with the non-uniformly hyperbolic sets. So you won't be surprised if I tell you that it's related to behavior of Lyapunov exponents. So again, we have a surface diffeomorphism for this. CR is enough, R strictly larger than 1. Just to fix notation, once you have an ergodic measure, you have its entropy, H, and 2 Lyapunov exponent on surface. One is lambda minus, one lambda plus. I'm only considering measures with positive entropy, so lambda minus is negative, lambda plus is positive. And let's say that the Lyapunov exponent of the diffeomorphism are entropy continuous if you have some continuity for measures with large entropy. So each time you consider, you have a sequence of measures, ergodic measures, whose entropy goes to the maximal entropy, so to the topological entropy of the diffeomorphism, then assuming this sequence of measure converges, then the limit measure has to be ergodic. And moreover, the true property, this one, the Lyapunov exponents of these measures converge to the Lyapunov exponent of the limit measure mu. And so the criterion is that in this case, so this property is equivalent to SPR. Okay. Well, in fact, I am really interested to check SPR, so I will only comment on the on one direction. So how to prove SPR. For the converse, but it's based more on things I think Omri will talk about on Wednesday. So I put some indication on the proof, but I hope you won't be frightened, and then you can skip this slide after because I will talk about something else. Okay, so the idea is that you have a sequence of measure converging to. Sorry, you want to check that you are SPR. So to check that you are SPR, you have to fix some constant. You take chi first. So for chi, you take something smaller than the exponent of limit measures mu, and then you take epsilon very small. Okay, you have to check something for any epsilon. Okay, and so what's important now is the continuity of the exponent. How do you use the continuity of the exponent? Well, when you have a sequence of measure nu k that converge to a limit measure mu, you have the oscillated splitting of the sequence of measure. A priori, it may not converge to the oscillated splitting of the measure mu, but of the limit measure. But if the exponent converge, then they have to converge on set with arbitrary large measure that they converge. Otherwise, you lose on the exponent. So this is how we use the convergence of the Lyapunov exponent first. Then for the limit measure, well, it's non-uniformly hyperbolic, but if you take a big time, then on a set with big measure, you have a uniform estimate, meaning, so if you fix some time n, then for instance, along the stable manifold, you will see a good contraction in time n over a set of points with large measure. And this, you can pass it to the measures close to the nu k. Why? Because the oscillated splitting converges. So you keep that in mind. You have on a set with big measure, for all the measures that occur here, you have a good bound on the contraction along ES and something similar along EU. And now we will have to build a Pearson set that has to have uniform mass for all the nu k. So for that, we will use a kind of Pliss lemma. So I think people in this audience are very familiar with Pliss lemma. So Pliss lemma tells you once you have a point, so in nu k, you have points whose Lyapunov exponent are given, then you look to times along the orbit where you see a good contraction starting from that iterate. So this is what we call the Pliss iterate along the orbit of X, and Pliss lemma tells you have a good proportion of iterate that satisfy Pliss that are Pliss times. But for that to have really good condition, you need that a bound on the derivative, uniform one. This is what is used in the classical Pliss lemma. Here we don't have a uniform bound, or this, you have a uniform bound, but it could be bad. It could come from some place of the manifold that you don't control. So here we use a different version of Pliss lemma, which uses a bound in measure. So we don't use it. We don't have a uniform bound, but a bound on the large set with large measure. So this is similar to Pliss, but it's in fact it comes from a maximal, the ergodic maximal lemma. Okay. Okay, so the conclusion is that you have, for all as measure in UK, a set with large measure of points which satisfy please estimate, please, which are please point, both for EU and ES. Okay, so if you remember the definition of Pearson set, here, yes, Pearson set, you're saying that for this point X, if you don't require this condition of K, for any time you have this estimate. Here you have X, here you have X. But for Pearson set, you also need this condition for a control for all iterates Fk. So for that, you need to, to add an argument. And so this is, for that, we say, okay, this set with please point has large measures, so the orbits will comes back with some frequency inside this set. And then you apply again please to find points which enter in this please set with some fixed proportion when you iterate L iterate. Bon, so when you apply this double please argument, you can build a Pearson set whose measure here you have a uniform estimate on this measure, independent on UK, and so this is this is exactly what you claim in this SPR property. Okay.
Sorry,
yes.
I have a question because.
So sorry for this technicality. I hope you will.
I think that you can define the entropy continuity if you assume that you are in higher dimension and you have several Lyapunov exponents and you have convergence for all the exponents.
Yes, yeah, you could define something like that, but it's more delicate because you have several directions to control, and so.
Okay, but no, okay.
Yeah.
My question is, assuming that you have the control of the direction, the conclusions of the criterion are true, or what is
this I don't know, and
because all the ingredients that you put in your argument, the 5 points, I guess that they are.
I don't know, because okay. Think that you take a hyperbolic set, a uniformly hyperbolic set, and you want to say it's SPR. Whereas if you have, for instance, a stable direction which has dimension 2, then inside you don't have continuity of the Lyapunov exponent. So it's delicate. I don't know. But
you went to the point. You went to the point. Okay.
Yeah, I use strongly the that I am on surface. Of course, in higher dimension, of course, it's what we want to do after. But I don't expect to have something so general. I expect that you have to restrict to some subsets. For instance, assume partial hyperbolicity is one weak. Yeah. But yeah.
Thank you, Sylvain.
Yeah.
Sorry for the.
Okay, so remember what I want to prove is SPR, so I have to check this entropy continuity. Okay, so now I change a bit. I want to discuss continuity of Lyapunov exponents. How to check entropy? Yes, this continuity. Okay, so I will present a different result that combines with the previous one. So remember, we have the measures, we associate the Lyapunov exponent. The Lyapunov exponent in general does not vary continuously with the measure. You have a semi-continuity only, but it's continuous for hyperbolic diffeomorphism on surface, not in higher dimension, but on surface. Okay, and you wonder in which case you can show continuity. Well, there are many works that discuss that. Many ones discuss this when you consider cocycles. For abstract cocycles, you fix a base, which may be a shift or a rotation, and then you look to the cocycle, you vary the cocycle, or if you have the shift in the base, you vary the measure in the base, and you look how the cocycle, what are the Lyapunov exponent, and then there are results. I have quoted some one thing which is a bit different is this result by Dujardin. It's for polynomial automorphism of C2, and he considered the measure maximizing the entropy. We know it exists for polynomial automorphism. And in this setting, he could check some continuity. Okay. So this is for exponents. And if you look to entropy, we also know that entropy is not continuous in general. So it's not lower continuous, never, because a measure may be approximated by periodic orbits. Whereas for upper semi-continuity, Newhouse, using Yomdin arguments, proved that it is realized when the diffeomorphism is infinity. So for infinity diffeomorphism, you have some similar behavior between Lyapunov exponent and entropy. And also, it's well known that you have some inequality between entropy and Lyapunov exponent, which is a real inequality. Okay. So what I will present is to say, okay, in general, when you vary the measure, you have these discontinuities, but we can compare the defect of continuity of these two invariants. So here is a result with Jérôme and Omri. So still for C-infinity surface diffeomorphism, look to a sequence of ergodic measure, okay, converging to a measure mu. I assume also to simplify that mu is ergodic. Up to take a subsequence that assume that the exponents, Lyapunov exponent converge, the entropy converge, and assume that this quantity are non-zero. Then how to measure the lack of continuity of the entropy? You take this quotient, entropy of the measure divided by entropy of the nu k. And so you have this inequality. So here, the first inequality tells you the semi-continuity you can have. And you have an inequality between these two behaviors. So for instance, if the entropy converge, the entropy of the nu k converge, this quantity converge to 1. So you have 1, 1. And so in the middle, it converge also to 1. The Lyapunov exponent do converge. So if a sequence of measure converge in the sense of entropy, then the Lyapunov exponent do converge also. So this is the result. And so it's exactly what we need for entropy continuity. Take a sequence of measure whose entropy converge to the topological entropy of the diffeomorphism. Then by Newhouse semi-continuity, the limit measure should have the limit entropy. So you have convergence of the entropy. And so you conclude from that the convergence of the Lyapunov exponent. And so you can check the criterion and deduce SPR. Okay. But I presented this result, then you have a more technical statement when mu is not ergodic, and even when the diffeomorphism is CR, so you have other version. So this is in a preprint we put on archive last spring. So yeah, yes, I have still some time, right? I can comment a bit on. So first, some amusing consequences, maybe. So let's talk about physical measures. So I recall the definition. You look to measures whose basin, so points whose Birkhoff average converge toward the measure, has a positive Lebesgue basin. So basin is positive Lebesgue measure. And so if you have a C-infinity surface diffeomorphism which has this property, so you have measures whose entropy is bounded away from 0, and for which you can define a pressure. So this quantity, so for each of the measure, you look to the difference between the entropy and the upper Lyapunov exponent, and you assume that the supremum of this quantity is 0. Then you conclude that the diffeomorphism has an ergodic physical measure. Okay, so in fact, behind that is the fact that if you have an ergodic hyperbolic physical measure, then this quantity has to be 0, has to vanish. And for any measure by real inequality, this quantity can never be positive, okay? So in some sense, you can pass to the limit over this measure in this quantity and find a physical measure at the limit. Another consequence in the same spirit, for a measure, you can define its Hausdorff dimension. So this is the dimension you can, the minimal dimension you can get for sets with a large measure. And so you look how this dimension vary over the set of measure, and we conclude that this dimension vary upper semi-continuously. Well, you have to be careful. You have to only to work with measures whose entropy is bounded away from 0, and you have to restrict to ergodic measure. So these are some consequences. Okay, I'd like to tell a bit about the way we can prove our control of continuity. So this is what we want to show, how to relate the lack of continuity between exponent and entropy. And so there are two things to say. One is about exponent, one is about entropy. So about exponent, how to interpret the discontinuities. So one good thing to do with measure is, okay, measures are on the manifold, but you look to the unit tangent bundle, and you may always lift an ergodic measure as ergodic measure on the unit tangent bundle. When the measure is hyperbolic, you have two lifts. One correspond to the mass. For one, the mass is concentrated on the unstable direction. So this is you will call it mu plus. The other one, the mass is concentrated on the stable direction. And so if you have a sequence of measure nu k that converge to mu, when you lift it, you look to the unstable part for the nu k, and you look how they converge on the lift. And so they have to converge on some barycenter between mu plus and mu minus. And this barycenter, the coefficient in this barycenter, exactly tells you what the Lyapunov exponent of the limit of the nu k has to be. So the upper Lyapunov exponent of the nu k, instead to converge to the upper Lyapunov exponent of mu, it converges up to some correction in terms of the difference of the Lyapunov exponent of, sorry, here it's mu, of mu, times this proportion alpha in the barycenter. Okay?
Sylvain, sorry,
yes.
These two ergodic lifts, what is this? What are these?
Okay, so let me say again, you have a measure on the surface. Then this, for the surface, you look to the unit tangent bundle, which is a compact manifold. You have a dynamics on the, yeah, I didn't say that. You have a dynamics on the unit tangent bundle, which is induced by the tangent map of the diffeomorphism. And so the invariant measure on the unit tangent bundle projects on invariant measure on the manifold. And when you have an ergodic measure on the manifold, you always have ergodic measure on the unit tangent bundle that lift them. This is general in abstract ergodic theory. You can lift ergodic measures. But when the measure is hyperbolic here on surface, you exactly have two ergodic lifts. No more, no less. Okay? One corresponds to the stable. So at each point in the manifold, you have one stable direction, which gives you 1 point in the unit tangent bundle, and one in a stable direction gives you 1 point in the unit tangent bundle above this point. So there are two ways to lift the measure, which are two ergodic lifts.
Okay.
Okay. So I like to write this convergence like this. The upper Lyapunov exponent of the nu converge to the upper Lyapunov exponent of mu times some coefficient beta that is satisfy this formula involving the barycenter coefficient alpha and the ratio of the Lyapunov exponent of mu. Okay, so this is to explain the the discontinuity of the measure. For the entropy, the way to control the entropy is first to so entropy is to measure the orbit separation. How many orbits separate? Yes.
So this item 1 here, is this kind of general nonsense, or this is a theorem also?
Well, it's something which is quite well known.
Okay.
But, yeah. You have to check something. You have to prove it. But it's quite well known. Yes.
Okay.
Okay. So about entropy, instead to look to how general orbits of the measure separate, you have the work of Le Drapier-Young allows you to concentrate on unstable curves. So you will take a piece of unstable curve, iterate, and inside the curve, you look to typical point for the measure and look how many different itineraries you see inside this curve. And so you will work with unstable curve. Usually to compute entropy, you will introduce bow and balls, and so count a covering by bow and balls. Here, instead to work with bow and balls, you will so you will push your unstable curve. So it will grow, it will fold, and you will need to look to parametrization by subcurves such that the parameterization are bounded, have derivative bounded. And you count how many parameterization you need. And it's a way to bound the number of bow and balls you need. And this is the approach of Yomdin and then of Newhouse to control the entropy using the fact that you're CR or C infinity. Okay, this allows so to involve CR smoothness and also to check that you can work with entropy at a scale which do not depend on a UK. Okay, so those are the two ways to control so exponent on one side, entropy on the other side. And the last thing I want to say is then you look to typical orbits, to typical points for the measure in UK, and you want to, so you decompose the orbit into two kinds of periods. Of course, the orbit has to spend time close to the limit measure mu, which has some expansion, some unstable direction. And so this unstable curve sometimes is aligned with the unstable direction of the limit measure mu. And so you will see some expansion and some separation of orbit. So you have some time where the unstable manifold is aligned with the unstable manifold of the limit measure. This is what we call unstable periods or unstable blocks. But you also have times where the curves may align with a stable direction. And so you won't see expansion, you will see contraction. And so the orbit do not separate during this time. So you see some contraction. And immediately after contraction, maybe you will recover, you will then bend and go in the unstable direction again and see some separation. Yes, Misha. And then the orbit are allowed to separate again. But since you first spend time close to the stable direction, the orbit were very close together. And so even if you're along the unstable, before separating, you need to kill the contraction you have seen before. Okay? So these are the neutral block. From one point, you say you have a neutral block. If when you iterate from this time up to another time, the derivative does not expand at all. So this is maybe because first you have some contraction and then some expansion, but until the time the expansion recover what you have seen during the contraction. Okay, so then you need to analyze during this neutral block, you don't see orbit separation that don't contribute to entropy. So to have entropy, you need to look to these unstable blocks. During unstable times, you have the same orbit separation at the limit measure mu. And so you have to analyze the frequency of iterates you spend near the unstable block. You compute, and this is, you realize it's the same beta that appeared before that control the Lyapunov exponent. So you have linked the limit behavior of entropy and of exponent. Okay. So this is what I wanted to say. As a conclusion, we have defined SPR diffeomorphism. We have checked that C infinity diffeomorphism with positive entropy are SPR. And on Wednesday, Omri will deduce some ergodic property. Okay. So thank you. Happy birthday, Lorenzo.
There were plenty of questions, but maybe we have time for one short question right now.
Maybe I think that Sylvain started his talk about talking about the homoclinic classes that intersect. I think that all the examples that I know, when you have two homoclinic classes that intersect, two different homoclinic classes that intersect in a non-empty set, the set always have zero entropy. Well, of course, you can cook some examples, but I think that this is the general principle. Do you agree with this or not, Sylvain?
So you think on surface or in
no, in general? In general, I think that in surface, essentially, you are proving that.
Because in higher dimension, you may have a submanifold.
Okay.
Separate two classes, and in this submanifold may be a surface, and inside you may have entropy.
There are examples like this that you have two classes that intersect along a horseshoe. But I think that these are the only examples, you know.
Yeah. So, and on surface, I don't have.
I think that in surface you are proving essentially that this is the intersection has zero entropy.
Yeah. We proved that the intersection has zero entropy, and yes, in higher dimension, I imagine things complicate may occur. Yes, you imagine there's so many fold, but then you may have some ugly intersection set. So I think that Misha is impatient. So sorry.
Okay, let us stop here.
Yeah. So.
It's not me. It's the cruel world that we are living in.
Yeah.
Okay, let's thank the speaker again.
Thank you.
And 12.